Hey, so today's video is an expansion of a talk that I'm giving about geometric impossibilities. So what that means is essentially we're going to talk about, the ancient problem about taking a compass and a straight edge and trying to construct certain geometric figures. And what we're going to focus on is those figures that are impossible to construct and the journey that it takes to prove those things. In particular, some of these problems laid unresolved for nearly thousands of years. But the first two videos is going to be just about the bare bones construction, something that most people could follow along with, and then the second half of this mini series is going to be about the beautiful application of abstract modern field theory and how that allows us to prove that some of these constructions really are impossible, and in some cases prove that some certain classes of construction are possible. But of course, before we get to this field theory abstraction, we're going to have to dive into the hands-on. What does it mean to actually construct with these things? And one thing I want to address really quick, something that confused me when I first heard about this was, well, why just a straight edge? Why not use a ruler? Well, one way you can think about this is imagine there was a time when there wasn't, say, the standardized meter. I mean, there was some sort of standardized distance, but that's the thing, is you have to arbitrarily set this standardized distance somewhere, right? And so we may as well start from that very practical beginning, that sort of bare bones assumption, sort of like when we're doing set theory. We start with these basic axioms and we see how much utility we can get while minimizing our starting assumptions. One of the other things we're going to see too is that actually we can sort of reconstruct rulers as long as we're willing to just sort of set our own unit distance to begin with. So it's not so much that rulers have to not be allowed in this construction, it's more about not being able to pinpoint specific numbers before you've actually demonstrated that you can construct those numbers. And it's a very similar reason as to why we, just use a compass instead of allowing ourselves a full-blown protractor. For example, 20 degrees is marked on a protractor. We're going to see that might not be so easy or even possible to construct such an angle. So in order to start talking about those things which are impossible to construct geometrically, we're going to spend this first video looking at those things that we can construct, and we're going to take a hands-on approach. The next video, we're going to dive into the abstract field theory that allows us to prove that the things we're going to claim are impossible really are impossible. So as a first example, we'll see why this is true in a moment. One of the things we can construct with the straight edge and compass is, as I mentioned, we can come up with our own unit length. We're going to see in a moment that we can actually create perpendicular lines, and therefore being able to repeat this unit distance, we can construct something that has the length of square root of 2. So we would say that the square root of 2 is a constructible number, as we've constructed a shape who has that number as the length of one of its sides. So we see immediately that the collection of those numbers which are constructible can even contain irrational numbers. So what are the geometric impossibilities then? Well, the sort of main famous results of these are, well, the first is trisection. So the claim is that there exist some angles such that there's no way, only using a straight edge and compass, that you can determine two lines which equally divides that angle into three pieces. There is also the impossibility of doubling the cube, which states that given some cube of, say, unit length, it's impossible using straight edge and compass. Again, of course, we're imagining doing this in a three-dimensional sense, or even just the two-dimensional representation of such a cube. The claim is it's impossible to construct a cube which has exactly double the volume of the unit cube. Perhaps one of the most famous of them, and one that crackpots online love to convince themselves that they've actually been able to do, even though it is impossible, is to square the circle. So the goal of this would be to construct a square which has the same area as a circle. Of course, we can reduce this to, again, the unit case. So that would amount to constructing a square of length square root of pi. We'll see that that's impossible. And then the very interesting theory of constructing n-gons, specifically regular n-gons. So things like squares, pentagons, hexagons. Well, everything I just listed there is constructible, but for example, a 7-sided regular polygon is not constructible. So that's something we'll be taking a look at as well. So to begin, let's see how we can actually recreate the notion of a ruler in this world and see how really to get it fundamentally. Well, of course, I can take my straight edge and bear in mind, even though these numbers are on here, I don't have access to an actual straight edge, but we're not going to be using these numbers, so I'm not really cheating here. I can draw an arbitrary line, and what I can do is, just select some sort of point, and I can declare this to be my origin. And from here, of course, I can also just open up my compass to any old distance I like, and this will be us setting a fundamental unit. So I'm going to declare this to be a distance of 1. 1 what? Well, 1 of itself. I'm declaring what the fundamental unit is here. And then the first thing to note is that we can copy distances, right? I can just keep my compass opened up to this size, put the point anywhere I like, and just repeat this exact distance anywhere. So immediately we see that all the natural numbers are constructible, right? For instance, going from here, from the origin to here would be 3, and I can repeat this process indefinitely. This will also allow us to coordinatize our system, right? So I can consider this, to be the number 1, the number 2, so on and so forth. And then I can consider everything to the left of the origin to be the negative numbers. So more than just the natural numbers, we can consider that all of the integers are constructible numbers. And this is actually going to lead us to a more general definition. In fact, we can even reconstruct all of the Cartesian system. Well, not in the full real numbers, as we'll see, but this brings us to the next important construction here, and that is the perpendicular bisector. So what we're going to do for this, let's say, we could imagine a priori we didn't know where this origin was, and let's say I just had these 2 points here. And I want to find the line that, well, first off, I want to find the point that's in the middle. And secondly, I want to be able to construct right angles. Well, one way we can do that is first, you basically eyeball where you think is past the middle. And in fact, you can open your compass up basically as far you want, as long as it's sufficiently far. And holding that compass fixed, you're going to make an arc. You don't need to make a full circle. Ooh, almost lost my spot there. But you can make this arc. And then the important thing here is you're going to keep the compass the exact same distance, and you're going to move the point over to the other point where you're trying to bisect. And you're going to make the arc and extend it just long enough that you get 2 points of intersection. And now my claim is that the line that passes through these 2 points of intersection meets the line at 90 degrees and perfectly bisects. So let me just draw the line first, and then I'll justify that claim in a moment. So drawing the line here. Now, before I finish justifying that claim, let me just point out that now here we get, our Cartesian coordinate system, because I can go back and simply readjust my compass to this unit length I had already constructed. And now I can make a unit length up here. And this leads us to our new, so of course, going up would be, a positive y-axis. Going down would give us our negative y-axis. And this gives us a new definition of constructible number, which is equivalent to the old one. And that is, we say that a number is constructible if I can construct a point whose coordinates in this system is a pair of a constructible numbers, or rather, if x is constructible, that means I can make a point that has x as one of its coordinates. I can construct that point. Okay, so we still need to justify my claim about the perpendicular bisector. So what we're going to do is join the points of this creation together. and I'll be able to argue it from there. So just connecting each one of these points. By the way, if you're following along at home, I mean, if you got I connected the wrong line there. But if you have a compass and a straight edge, highly encourage you to follow along at home. So what we have here is a rectangle, you'll notice. And now it makes it easier to see why this is true, right? Because we have the two lines which pass between the corners of the rectangle. And now it's just some reasoning with high school geometry, looking at each of the angles through here to prove that yes, these meet at a 90-degree angle, and this perfectly bisects this line. Okay, so we're able to recover our Cartesian coordinate system. We have a new definition of constructible numbers. We know that we can cut lengths in half, and we know that we can create 90-degree angles. So another really important thing here, the next step in this process, is going to be the fact that we can divide any constructible number by any integer. We're going to get to a more general result in a moment, but you'll see in a few minutes why we need to do this first. So to begin, we take, you just make an arbitrary angle of lines, doesn't matter. And on this line on the bottom, you construct, so let's imagine that we've constructed our number n. So n here is just going to be some constructible number. It doesn't matter what constructible number that is. We're showing that this works in general. And then what you're going to do is along the top here, you're going to take your unit length. So I believe my compass is already still set to that unit length. And you're going to make a bunch of copies of that unit length along this top line here. So I've got 1, 2, 3, 4, 5, and 6. So for this example, and you don't necessarily need to go past n. In fact, well, I will. Let's go 7, right? So in this example, we're going to construct the number n divided by 7. But really the point is you can construct n divided by m for any natural number m. You just repeat this process as many times as you need to get m. And what we're going to do here is take the point of the endpoint of the final distance we want to divide by, and connect this to the point that is at distance n from the angle. Okay, so embedded in this construction is the very important angle copying process here. So how that works is, let's say I have this angle along here, and what I would like to do is copy this angle. So that is, I would like to figure out how to draw a line down here or from any of these other positions such that the angle made between this line and the new line is the same as this original angle. So the first thing I do is I put the point of my compass on the middle here, and making this a little bit smaller, I'm going to draw an arc that I want to make sure that this arc I'm drawing crosses both of the lines that I'm interested in. So I'm going to draw this arc here and see it crosses both of the lines. So I'm going to go here and I'm going to make sure, I'm going to put the point of this compass, it was just on this angle, I'm going to put it on that point that I want to be the new corner of the angle. And I'm going to make sure the arc crosses one line and goes past, you know, where I think the other one will be. When in doubt, you know, if you have to make an arc, you know, I have some experience at this, I'm eyeballing it. So if you have to make an arc, you know, when in doubt, you can always just make the full circle. You want to make sure that lines go further than you think they have to when you're making these geometric constructions, because it can be a real mess if you have to go back and try and recreate them later. So just making this final arc over here. And now, in order to finish copying the angle, I'm going to set my compass open to these 2 points here. So that is the 2 points where that arc I made intersects the 2 lines. And now, perhaps I should set it up this way, although it is symmetric. Now the point is, notice that this is where the point is that this point of intersection. I'm going to move this over to this point of intersection here, and I'm going to find the point where these arcs intersect. And again, I'm just going to copy that every step of the way here. And now my claim is that the line from the point where we're trying to create a new angle and these new intersection point, my claim is that that line is creates the exact same angle here. So let me draw all of these in first. Okay, now that I've used my superpowers of time travel to finish drawing in all these lines, you can see some places it's a little imperfect, but we're going to justify why this is the right construction. Imagine, right? Think about the triangle that exists here between all of these points. So from this first arc that we drew, we know that both of these lines have the same distance. And then since what the compass is, right, it collects all the points wherever you put the center and open it up to, it will give you all the points at that same fixed distance away from that center. So when we move the center over to say here, we see that along this line of intersection and along this line coming out of it, both of these, the distance from that center to where they intersect the arc, must both share that same distance and be this same distance here between these two. And then remember, we had opened up our compass to get the length between these two points of intersection where the arc meets the 2 outgoing lines. So this little dotted line I made through here, I'll put a double dash here, because remember, we copied this distance between these 2 arcs over here. That's where we got this little mini arc. The compass was measuring out that distance. So if I were to think about the triangle made by all 3 of these points here, I get this double dash here. And so now you see that we actually have a pair of similar triangles, right? These lengths are all the same as these lengths, and therefore all the angles must be the same, namely these 2 angles must be the same. So we have in fact copied the angle. So that is an important construction unto itself. But now we see here in the larger picture, what that means is following through all of these same arguments. Of course, that means that, just doing some simple angle chasing from high school, that all of these angles along here are all the same. And so namely, because each of these distances we know is just a copy of the unit distance, that is, we've evenly divided the distance from this lower point down here to this upper point by 7, we know that we've now divided this distance from here to here because each of these lengths must be the same, whatever length that happens to be, by 7. And therefore we've constructed n divided by 7. And of course, as I mentioned, we can repeat this process to obtain n divided by m. Okay, so I think for the sake of brevity, I'm going to end the video here. And in the next video, we're going to look at how to divide general constructible numbers. So we show that constructible numbers are closed under division. We'll also talk about multiplication and square roots. And I suppose we'll save the field theory for the 3rd video. Again, if you have any questions, comments, concerns, please don't hesitate to mention that in the comments. Thanks.